I don't know how you guys make it through this quarantine. What are these? Say hello. Hello. There she is. There she is. Oh, look at that. 1.5 pounds of amazing weasel. She's so lazy. All right, picking back up where we left off. So I've summarized e to the x. Remember, that's the Maclaurin series. Everybody would call it a Taylor series. But if you want to be specific, since we expanded around little a equals 0, it's a Maclaurin series. Now I'm going to do for sine x, f of x equals sine x. And we see one of the biggest ideas in math. It's a very strange idea that you're about to see. So let's take repeated derivatives of sine x. There they are. And if you remember with sine x and cosine x, the repeated derivatives, you get back sine and cosine, but there's these minus signs and they don't alternate. Remember, do you remember? You get a couple of minuses in a row. See? A couple of pluses in a row, a couple of minuses in a row, which is very strange. A lot of things in life alternate left and right, left, right, left, right. All right, there you go. And anyway, so let's evaluate each of these guys at a equals 0, and you get a 0, a 1, a 0, a negative 1, a 0. I can see what's going to happen. I'm not a moron. It's going to be 0, 1, 0, negative 1, 0, 1, 0, negative 1 for the rest of its life. That's the coefficients. Now you're going to have powers on x to the first, but that goes, remember, it's 0 for the constant, 1 for x to the first, 0 for x squared, negative 1 for x to the third. So this is the pattern, x minus x to the third, not two minuses, plus x to the fifth over 5 factorial, don't forget the factorials, minus x to the seventh over 7 factorial. So you have an alternating power series. The downstairs get really small, really big, really fast, so the fractions get small, which kind of makes sense because remember, sine x doesn't do very much. It just bounces between 1 and negative 1. That's the power series for sine x. You can do cosine x, the same kind of thing. You take the repeated derivatives, and here's the power series for cosine x with the, I forgot the dot, but you know it's there. Now let's check both of these two things out. They reveal something that we kind of already knew. I don't know if you remember, sine x acts like an odd function. Sine of a negative is the same as negative of the sine of the positive. So if you wanted the sine of negative 30 degrees, it's the negative sine of 30 degrees. Sine acts like an odd function means the negatives survive. An even function eats negatives, like negative 1 to the second power is 1. Cosine is an even function. And look at even powers. Look at sine, odd powers. Isn't that weird? We see properties that we already know in terms of the Taylor series. It's a beautiful idea. Now, when people were doing this math, it was late 1700s, mid to late 1700s, de Moivre and Euler both noticed this thing. They noticed that, hey, wait a second, e to the x, sine x, and cosine x are welded together. They have a very cool relationship, but you have to go to the complex numbers to see it. And if you remember, the square root of negative 1 is I. So I to the first is I squared is negative 1, I cubed is negative I to the fourth is 1. Here's a way of getting two minuses in a row and then two pluses, because it would go I, negative 1, negative I, 1, I, negative 1, negative I, 1. That's how the series would go. That it takes on this weird effect that we get from the derivatives. And then they notice that, okay, if you do this series for e to the x and you put in I theta for every x, in other words, you go to the complex numbers, you put in I theta for every x, it will match exactly as if you put thetas in for all of these and I thetas in for all of these. The minus signs and everything would all match up. So this was a very big formula because it ties together E and I and trig. Nobody saw that coming. When that came out, everybody said, whoa, are you kidding me? Are you kidding me? All these ideas are stuck together. And this formula means you could take, put in a famous number for pi, or for theta, pi or pi over 2, pi over 4. You can put in numbers for this theta, and you get a very simple thing. You get a very simple result. Anyway, so that's a famous idea. Now I'd like to use some Taylor series. Hang on. Carrying on. Here's some homework. And you say, homework, the semester's over. Look, semester's over next Wednesday. I can still give you homework. Ha! So, go to the section on power series, try some problems from 15 to 29. Go to the section on Taylor series, try some problems 13 to 19, and feel the power that you get from power series. It is so cool. So enjoy. Have a good time with these things. Now, one of the problems from this section, they'll give you a polynomial like 3x squared minus x plus 1, ask you to find its Taylor series around a equals some number. I made up this one. 3x squared minus x plus 1 around little a equals 2. Now, if you're smart, you know what the answer is going to be. So think for a second. Think. And now we're going to do the problem. So how do you do Taylor series? You take repeated derivatives. Well, a little polynomial like this is kind of nice because as you take derivatives, you get down to the third or higher derivative, they're all 0. So I just took repeated derivatives, and now you have to do f of 2, f prime of 2, f double prime of 2, and you can stop there because f triple prime, f, the third derivative and onward, is all 0. So you wouldn't be doing those terms anyway. So it's a finite series instead of infinite. So I did these evaluations. Putting in a 2 for this x and this x, I get an 11. Putting in a 2 for this x, I get an 11. And putting in a 2 for, well, there's no x to put it into, the function just gives me 6. So I put those in, and I do the definition of Taylor series. I do it way over here. Let me get out of the way so you can see it. So you got the first term, and that's times x minus 2 to the 0 power over 0 factorial. So that's just a buns naked 11. She yawned. Let's get her back in the picture. There we go. The next term gets a factor of x minus 2. And the last term gets a factor of x minus 2 squared. Don't forget to divide by 2 factorial, which is 2. All right, now I expanded the x minus 2 squared. It's right there. And let's finish this. Let's see what we get here. I've got a 3x squared. No other x squareds. I get an 11x minus 12x. 11x minus 12x is minus x. And then I have 11 minus 22 is negative 11 plus 12. Negative 11 plus 12 is a plus 1. Oh my God, we got the original function back. And it's because, what does Taylor series do? It gives you the polynomial version of your function. So if the polynomial, if the function you have is already a polynomial, then you're going to get back that polynomial, which is a very easy problem. Can you imagine this being on a test or on a final exam, you know, that give me the Taylor series for this polynomial around x equals 11. Don't do any work. It's going to come out to be the same polynomial. It's pretty nifty stuff. Yeah, so that's a cheesy example of Taylor series. Let's do a less cheesy. All right, typical problem for you. Instead of just e to the x, we have e to the 2x. And it's actually easy power series. It's actually really easy because we already know the power series for e to the x. So if you know the power series for e to the x, you literally get to substitute a 2x for every x in the power series you already know. How great is that? You don't have to take all the derivatives and do all the stuff. Just pop in the 2x. And now we'd like to find out, oh, and this is around little a equals 0. I didn't even write it down. So we'd like to find out its radius of convergence. Well, you need the formula for the general nth term. You got to be able to figure that out. And for most of the tame functions that you have in your calculator, finding that nth term is not so tough. It's interesting how often a famous function that was defined way before calculus turns out to have a really nice Taylor series. It's kind of weird. It's almost like all the math pieces that we know fit together nice, and then the future ones will also fit together nice, as if math is like a prefab building and all the pieces fit together nice. It's not like, you know, you got a bunch of rocks and you got to glue them together to make a cave. You got to make some kind of shelter, like, you know, something, and you're just mortising these rocks together, and it looks like crap. And math isn't like that. It's very cool how the structure's nice. Anyway, so let's say we wanted to find out the radius of convergence. We want this ratio to be less than 1. So I did the typical thing where instead of writing the 4-story fraction, I have the first fraction times the flip of the second. And a really nice thing happens when you have n factorial divided by n plus 1 factorial. Let's think about that. This guy is n times n minus 1 times n minus 2 times n minus 3 times dot 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 times 3 times 2 times 1. And this guy is n plus 1 times n minus 1 times n minus 2. So the only thing that survives is an n plus 1. And then look at these powers on x, powers on 2x. I have a 2x to the n plus 1, and I have a 2x to the n. All of them cancel except for one little skinny 2x. So let's go take a look at that. all that's left is a 2x over an n plus 1. And my n plus 1, or sorry, my n is going to infinity. So what's that limit? For any x, that limit is 0. And you say, well, couldn't x be a billion? Yeah, and what's a billion divided by infinity? 0, Jack. So this limit is 0, which is less than 1 for all x. And that's not x factorial, that's x. I'm just putting that exclamation mark on there for emphasis. This happens for sine x, cosine x, e to the x. You have infinite radius of convergence, which means that e to the 2x can be written as this. And it's exact for any value of x. But you have to have the infinite series. You have to have the dot, dot, dot on the end. So the book does a famous picture. You'll see this in a lot of places, where if you only do 12 terms, what you do is, if you do 12 terms of the graph of the 12 terms looks like the graph of e to the x for a piece of the x-axis. And then the two functions don't look like each other anymore. And that's not radius of convergence because you only did a finite number of terms. So if you're looking at those pictures in the book, remember they're just adding terms and showing to you that as you add more terms, this sum resembles this function more and more. And then this here is the evidence that the infinite sum is exactly this function. This equal sign is not an approximate. So there you go, guys. Go play with Taylor series, power series. Let me just tell you what I'm going to do. You're going to get a take-home test on this last chapter. It's going to be due when the final exam is due. So you got 2 more grades. This take-home test, which is untimed, take it whenever you want, and then the final exam on schedule. Bye.